Okay, good morning. Today we will discuss how to simulate the flow of blunt bodies. A cylinder is one of the blunt body that we see regularly. There are many other blunt bodies like all our buildings. They are also blunt bodies. Why they are called blunt bodies is as the flow you can see here as the flow is passing over through this body. At this point, we'll get a stagnation point or the fluid velocity comes to rest. And as the fluid flow over the body, here there will be flow separation, and if it is a streamlined body, the shape of the body will be like it will be along these streamlines, so that there is no wake here. This wake is because of here there is a pressure gradient. Okay, so this as uh, here from here to here, if you see here, this area is more and here is area is less. So we have a uh, flow is happening in this direction from high pressure region to low pressure. Now here, in from here to here, if you see the area is increasing, so the pressure decreases. The pressure increases. So because the pressure increases, there we will see a wake that is forming here. So it is an adverse pressure gradient, and because of that, we are seeing some wake. So how to simulate this kind of flow in ANSYS or CFX? We'll see how to do this in CFX. Now, if you open this workbench, in that we have the CFX module. I have taken the CFX module. In that, I am going for design modeler for creating my geometry. Now, this in this design modeler, I am taking a plane. This I am selecting XY plane, and in XY plane, I am making a circle. I am changing the units to millimeters first. I am changing the units to millimeters. Then I am drawing the circle. This is the circle. Now I am giving some dimension to the circle. So the dimension is say suppose 24 mm, very small circle. Now what we have to give to the CFD analyzer is the flow domain. We don't have to give the cylinder, but the region through which the fluid is flowing, that region we have to give. That is why what I am doing, I am making a rectangle here. So this is the rectangle here. So I am drawing a rectangle. If I click on this y axis, it will change the orientation. So that is why it happened. I am taking little longer section, the downstream section. So this is called the upstream section, and this is called the downstream section. And okay, now what we have to do is we have to make the domain. For that, I am using the extrude command, selecting the sketch, apply, and add frozen, and I am taking some 50 mm, or I can take 100 mm also. So this side how much you may take, it doesn't affect much. So I am taking 30 mm, so that my simulation time will be less. So after this, after defining this, click generate. So this is the flow domain that is formed here. So this is the flow domain, and in this I have to make it fluid and generate. Now the fluid domain is, this is the fluid domain. So once this fluid domain is formed, so here cylinder is not generated, but the region around the cylinder is generated where the fluid is to flow. I am closing this and I am opening this mesh. Now this is the flow domain. In this we have to define the inlet. Right click on this, create named selection and inlet, and this is the outlet, and this is the surface of the cylinder. Three things I am giving: surface of the cylinder. Now once I give this thing, what I can do is I can generate the mesh. So for generating mesh, say suppose if I want to capture the boundary layer over the cylinder, if I have to catch the boundary layer over the separate cylinder. Now this as we were discussing, this is the flow domain through which fluid is flowing, and this is the surface of the cylinder. Now here if I want to capture the boundary layer over the surface of the cylinder, what I have to do is I have to give some inflation, and there are some calculations for that. For the dim by now I will just tell how to give the inflation. Inflation means what we do here is, this is the flow domain in which I have to make the inflation. Now this is the boundary on which I have to give inflation. So one face is selected, and here again I am giving number of we can give total thickness, or we can give the first layer thickness and smooth transition like that. So we will give the first layer thickness, and based on the velocity with which it is flowing and based on the diameter, uh, we will get the Reynolds number, and based on that we will give it entering the first layer height. So here what I am doing is I am just giving some finer first layer. So I am giving units as millimeters so that it is easy for us to give the uh, height here. 0.01 mm, 0.1 mm, or 0.01, 1 mm we are giving. I am giving here, and 12 layers I am giving. And now if I generate mesh, you can see what is the what do you mean by this boundary layer. See here, this is the inflation region where the first layer is of 0.1 mm, and then it is the growth rate is given as 1.2. So what happens is The second one is 1.2 times of the first one, the third one is 1.2 times of the second one, like that it will go on increasing. So with this we have completed the meshing. Now we will go to the simulation. So we have taken the length around from here it is approximately, here from here to here it is 20 mm and it is 80 mm, and another 20 mm, so another 40 mm. So 60 plus 80 it is around 140 mm length we have given. So based on that we'll update the mesh. When we update the mesh, you will get a tick mark here. The tick mark is there. That means the meshing is completed. It will take some time. Now go to the setup CFX pre. It is called. Here we will give the physics. What is the velocity and how is the boundary? All those things we will give here. This is our fluid domain. So inlet analysis type, you have something called steady state and transient. Steady state means with the time it is not changing, so we are taking only steady state. And in the default domain we are taking it as air flowing or water flowing, anything you can take. I am taking as air at 25, and the reference pressure is 1 atmosphere. And the domain, the, the entire domain is not moving, but only the fluid is moving through the domain. And model, it is K epsilon model is there, or we can take the SST model or BSL model, SSG Reynolds stress model, like that we can take. So we can take here, if at all you are interested in what is the flow physics through the this boundary layer, so we have to go for SST model. Now for the time being I am just going for the K epsilon model. And now I have to give the inlet boundary condition. Inside boundary, inlet, boundary condition, location, we have to select from this inlet, and then boundary, normal speed, the velocity with which the fluid is flowing over that. So I am taking as 1 meter per second or 0.5 meter per second. I mean with the different velocities we will get a different structure here. So we will take 1 meter per second, and keep it, click apply. And again the outlet I am giving outlet. Here the pressure condition is there, so the average static pressure here will be atmospheric pressure. If it is, the reference pressure is atmospheric pressure, and here also we need atmospheric pressure. So the relative pressure will be 0, because the yeah, that absolute pressure and the atmospheric pressure are same, 1 atmosphere, so the relative pressure is 0. Now here again another one is surface this, okay, this wall, you can take it as a wall or a surface. So if you want you can take it as a wall. The location is again surface here, and boundary layer is a no slip wall. Okay, the surface of the cylinder is a no slip wall. So what we can do, no slip wall means there is friction between the fluid and the surface. That is the meaning of no slip. And the wall roughness is very less. That is the meaning of smooth wall. Now solution control, high, the turbulence numerics and advection scheme, two things are there. Upwind you can take, or here you can take high resolution, and maximum number of iterations 1000 we can take, and here I am giving a 0.005 mm and making it okay. Now the output control, we don't, I'm not giving any additional monitors over here, so I'm just closing this. Now simulation, we can go for 4, since I have in my system uh, yeah, in my system I have 4 processes. Okay, so that is why I can go for a maximum of 4 process, 4 cores. Okay, and if I have more I can go for more, but here I have only 4, so I am going for maximum Intel local MPI parallel, and here I am going for 4. I am clicking double precision and starting. Now you can see here the there will, for every iteration there will be error, and the errors are monitored here, and these errors they will keep on reducing if the solution is converging. And see, these are the errors. Now these are different types of one. In mass, what is the error? In U momentum, what is the error? V momentum, W momentum, what are the errors that we have to see. When the errors are reaching 10 power minus 5, then the simulation will exit. Now I can close this, and I can go into the results. Now what we can do here, we can create a plane. And how is the plane? It is say suppose xy plane. So if I want the plane in between, so I can make it, I can bring it into the middle. And now on this plane, I will find the velocity distribution, velocity contour I am plotting, and in all domains, and on the plane one. If I apply this, here the plane is visible, so it is not so proper. Now here if you see this blue color one, here the velocity is 0, and here this is the stagnation point, and this is the wake region that we have seen in the beginning of this video. And here, now here if you want to see the streamlines, that also you can see, so that you can see how the things are going. I am going for the surface and plane, and starting from we'll see, we'll take some 50. If I switch off this contour, these are the streamlines. See here, these are the streamlines. If I increase the streamlines to 100, I can see more. Okay. Now say suppose if I make them location, if I give the wall as the location and make 100, then I can see that. See this. The the truth, I mean, on the surface of the wall, how the flow is happening, that is shown here. If I want the vertices here, then uh, so if I already, I mean, if I select some location here, so suppose if I take what we can take any of these locations. So suppose if I take a point cloud location, on plane will take, and will take, say suppose 10, not equally placed, uh, random. So here it has, okay, if I grid, now if I take this one, if I can select this, then I will get this one I will switch off. I will take a simple point here so that it is little more easy. So here, so the point is here. So if I want to move it in x direction, so now the streamlines starting from the point. Okay, if you see here, from this point, so many, I mean, the vertices are to be generated. So if we can see, uh, if I give randomly many points here, then we can see so many what to say, the wake region we can easily plot. We'll just see if we can create a line, 2 points. Okay, this is better one. We'll go for a point here. 0.009. Here also I am giving 0.009. But here what I will do, I will increase. See here, this is the line which is want to give me the point. Yeah, this is the line. So here I am taking, so suppose 2. So this is the 2, and I will increase this one little bit. Yeah, so it is around 16. So here also I have to put 6. So this is the uh, plane. So here what I can do, minus 0.05, and here also I will do. Now we'll see. Yeah, it has gone somewhere. Yeah, this is now if I see the streamlines from this line, you can see so many streamlines and like so will increase. So from these points you can see here, and if you create another streamlines starting from the wall here like this, by using number of streamlines we can easily depict the uh, streamlines. This is the and if I give more points here I will get more wake. If I don't give this wake I will not get. See, suppose if I don't give this streamline one, I will not get any streamlines because I have selected the wake region also, so I got some streamlines. So in this way, I can create. I mean, show the streamlines how the fluid is flowing through the flow or the cylinder. So this is about the flow or a cylinder. In similar way, you can you can simulate the flow or a flat plate or flow or a rectangular block or a house or any building area. So with that, I am closing this session. Thank you.